the program with Ali Yazdani. So probably for most of you, Ali does not need any introduction. Ali is one of the world experts on scanning tunneling microscopy, where in the past he examined a lot of strongly correlated systems like the cuprates, but also topological insulators. And of course, passing on from Alan's talk, all these phases seem to be existent in magic and graphene. So it's a wonderful system to study all those phases. And while Alan was giving a more of a theoretical overview of the field, Ali will also present some of the introduction on experimental investigation of this system. Thank you very much, Ali.
Okay, should I get started?
Yep.
I hope everybody can hear me. First of all, I want to thank ICFO and MIT for putting together this summer school. It looks like a wonderful program. I'm very happy to be included here. And I look forward to telling you about what we have been working on. And I was given a bit of instruction to do some introduction. So before I get started, let me just see if I can get the mouse to work as usual. It was working before. Hopefully my mouse is working.
It works.
Okay, perfect. So as a way of introduction, let me just remind you that kind of two of the important pillars in quantum condensed matter physics for the past 3 or 4 decades have been what electronic correlations and topology give us novel electronic states in materials. And I think since the 90s, early 80s and 90s, understanding the influence of correlations, such as trying to understand spin liquids and high temperature superconductors, have really dominated condensed matter physics. And of course, in the area of topology, quantum Hall physics, and then more recently, topological insulators and semimetals and superconductors have dominated much of the work in the field. And I think what's exciting about the Moiré systems is the fact that these broad class of materials, even graphene, so simple, is starting to give us a very nice platform to study both electronic correlation and topology. And I think the cleanliness of this material really gives us a thing that we were lacking, for example, in studying correlations in material systems that are doped. Here, there are material systems such as twisted bilayer graphene, which are chemically extremely simple, but they can be gated to study how electrons interact in 2D. So I'm going to give a little bit of a quick introduction, just emphasizing a few things that Alan said, and then moving on to the experiments. Here's, of course, the famous twisting plot that shows you the Moiré pattern that emerges when you take 2 bilayers of graphene and twist them on top of one another. The way to think about this is that, there are 2 sublattice sites, A, B sites on graphene. And, when you have very small twist angles, the A-B stacking can be such that the A sites can be on top of A sites in the middle of the regions of what you see in this Moiré pattern. And that smoothly transitions over what we call A-B stacking. That's basically what your eye is picking up. And as Alan pointed out, the essential thing here is that we can adjust the length scale, the periodicity of this Moiré pattern as a new periodicity to impose the electronic motion. And let me just remind you that we start with graphene, in this case, with these 2 Dirac cones. And also in the momentum space, we think about the twisting, basically the Dirac points that emerges in the graphene structure relative to one another. And now what we have here that gives us the magic is the coupling between the 2 graphene layers in the bilayer system. So in particular, if you just think about these 2 Dirac cones and think about how electronic states can hybridize with one another between the 2 Dirac cones emerging from the 2 different layers, you can think about this hybridization pushing down basically this overlapping of the bands emerging from these 2 Dirac points. And it's this pushing down that gives us, as you decrease the angle, the way I think about it, as the way in which the flat band condition emerges, as it was discussed by Alan in his talk. So this is plot from Alan's seminal paper, including here references to work by others who had done before them. So the key idea here is that at a specific angle, this theoretical study shows you that you get a perfectly flat band. And of course, what you want to keep in mind is the fact that what you have here is a superlattice Brillouin zone coming from kind of the Moiré structure. And that if you include a lattice relaxation, that was, for example, this questioned in the previous talk and discussed, this flat band structure actually kind of separates out more nicely away from what we call the remote band in this system. So now, let me just show you also a real space picture of what the electronic density of state you would expect to get from such a flat band structure. This is actually critical. So here is a calculation on the left, again, including the relaxation, showing the two flat bands. And these two flat bands basically have two spin, of course, and two values of degrees of freedom originating from graphene. And now if in real space you ask from these band structure calculation what the electronic structure will look like, it would look like, of course, it would resemble the Moiré lattice, but more importantly, you have these peaks in the density of states, which is telling you that the enhanced flat band density of state is living on the AA side in this Moiré lattice. So a way I kind of think about this problem is that because of the degeneracy of the system, you can think of these puddles where these peaks are places where you can put up to 8 electrons. So the convention I will use is the charge neutrality as being 0 electrons, and you can remove 4 electrons, that's -4, and you can add 4 other electrons into the conduction bands. So there is conduction and valence band, each of which fitting 4 electrons. And I always have fun thinking about, actually, the one slide is missing here. Even Alan's original paper, they anticipated partial filling of these bands, which gives rise to novel physics in this system. So of course, as you all know, the excitement in this area got started by the discovery by Pablo Jarrillo Herrero group at MIT, which basically built these magic angle 1-degree structures in gated devices in which you can adjust the carrier density into the flat band region. So what they did in this study, as you know, is they adjust the gate in order to partially fill these flat bands and look at what electronic states emerges in this partially filled flat band. And what they discovered was that at a partial filling of 2 electrons per conduction flat band and removing 2 electrons from the valence flat band, you get this correlated insulating state. So this was originally coined as a mod insulator. There's, as you know, quite a bit of interest to actually identifying the nature of the insulating state in these materials, which is something that we're still all working on. But what is exciting, of course, is that as you dope away from this correlated insulating state, is you get these superconducting phases emerging in this material system. And of course, the resemblance of this kind of phase diagram for electronic states to that of the typical correlated superconductor, for example, cuprates or iron pnictide or even heavy fermions, is one of the things that gets the attention of people like me who've been working on cuprates a long time ago. So in fact, what makes the resemblance even more canny is to actually flip the diagram here to look at that the whole doping of this insulating phase gives you sort of more robust superconductivity than the electron side. So these was early experiments which had been reproduced by a number of people, including the group at Columbia. But here I put results from ICFO, which is quite spectacular example of how this field is evolving as you make better and better devices. And what's shown here by our chairman is that as you dope away from charge neutrality for putting every, in my notation, 1, 2, 3, or 4 electrons, or removing 1, 2, 3, 4 electrons by nu here, you get a cascade of correlated insulating phases and also a number of superconducting domes in between them. So as if this was not enough, discovery of superconductivity and its prevalence near a correlated insulating phase. It's also the discovery by our colleagues looking at magnetism and topological phases that emerge in this system. So starting by work by Hubbard Gordon's group at Stanford, they basically discovered that near the filling of 3 electrons in the upper flat band, the system shows anomalous Hall effect. And later these experiments done also by Andrea Young at UC Santa Barbara, they observed that as you align their samples with the boron nitride layer underneath, which seems to be a key element in this discovery, they were able to observe the quantized anomalous Hall effect at relatively high temperatures. And as you heard from Alan, there's quite a bit of excitement about these Chern insulating phases and whether they are orbital magnetism that is giving rise to these novel anomalous quantum Hall phases. So this is also another area which is quite actively being studied by all of us. So I think as a way of introduction to the students in the summer school, I would say that this is a system which has correlations, it has superconductivity, and this topological phases that emerge in this system actually comes from the fact that the band structure of this system has the Dirac cone that has a Barry curvature that can get gapped and get a Barry curvature and have the topological property in this system as well. So there is quite a lot here to figure out. So this is a very exciting field to be working in. So what I'm going to tell you about today is how we use the scanning tunneling microscope to study twisted bilayer graphene. So let me just remind you quickly, we use the STM to obtain structural information in its typical imaging mode. We have a sharp tip, which we bring next to the sample, and we raster the tip across the sample, keeping the tunneling current constant while we adjust the height of the tip. This gives you the contours of constant electron density of state. It gives you information about the structure of the sample. Now we can measure the density of state as a function of energy to see if there are energy gaps or even get information about the band structure, as I'll show you in a second. And of course, we can spatially resolve this spectroscopic information by combining imaging and spectroscopy together. Now, the thing that is exciting to me is that the ability to gate structures and tune the electron density in them, and combining this capability with STM gives us kind of a new capability to study the physics of a strongly correlated system in these 2D materials, the Moiré system, in a device-like structure. So for example, in the high TC cuprates, when we wanted to study properties of some materials as a function of doping, we had to just basically create samples with different dopings as a function of how much doping you put in the sample, and study different samples. Here we have the ability to do this all in one device, one sample, which is a very powerful way of getting at the physics, getting around the doping disorder, and so on. So in today's talk, I want to show you how we visualize these states and show you the spectroscopy of how we resolve the flat bands that people talk about. And the main question I want to address here is sort of how correlated are the electronic states in this system. Now you saw that they have a lot of resemblance to the cuprates, the strongly insulating states. The correlated insulating states is an example of correlations from experiments that is very powerful. But here I'll show you the spectroscopic signatures of correlations. And also I'll show you, as we partially fill these bands, as we go through these integer fillings, as it was discussed, for example, in Alan's talk, in reference to changes in the sort of quantum oscillations, we can see that there's a cascade of transition that happens in the system as you go through this integer filling. And this has to do with the interplay between the quantum degeneracies in the system, the spin and valley, and the interactions. And I'll show you that, as we would expect, you can actually control the strength of this interaction in the system. And this is what I would like to talk about. And hopefully I'll get through that. And if there are questions about other things, I can try to address it as we go along here. So before I show you the data, let me show you who's responsible for all this work. This is a work that's been got started in my group with Yanglong, Berthold, Cheng Li, and Zhao Ming, doing the first set of experiments, which I'll show you about. And now The second set of experiments have been carried out by Dylan, Kevin, and Monchel, and we have collaborated very extensively with my colleagues Bia Lang and Andre Bernavik, the theorists who have helped us understand the experiments I'm going to show you today. So before I get started to our experiments, let me show you experiments that were done before all the excitement around twisted bilayer graphene. In fact, one could say that results from STM studies were very critical to drive people to look at this system. So these are experiments from Eva Andre in the early 2010 or so, 2009, where these are not gated structures. These are looking at twisted bilayer graphene layers on graphene. They were able to find with the STM spectroscopy that there were indeed sharp peaks in the density of states with very narrow peak structure and resembling sort of the flat bands that the theoretical studies had just beginning to anticipate. And a little bit later, before the excitement in transport, STM studies by Mike Cromie's group and Dylan Wong, they showed us that as you actually change the twist angle, which is, you can read off here from the periodicity of the Moiré lattice. The Moiré lattice periodicity depends on the angle between the two layers. You can see these Van Host singularities associated with the density of states of the system basically being tuned as a function of the twist angle. So what's nice about this, and this sort of fitted very nicely to the theoretical picture that was being developed by Alan and others after this initial work by Eva Andre. So what I'm going to tell you about is how we do the similar experiment, except now we are making gated structures, just like our transport colleagues have. So you'll hear from our transport colleagues in this conference, in this school, who basically invented the techniques of creating these twisted bilayer in a rather precise manner. So we have used what they have invented. This is essentially using the methods of using some sort of a polymer. And of course, the critical thing you want to build everything on is hexagonal boron nitride. And you use this hexagonal boron nitride that you've picked up with this polymer stamp and to tear off pieces of monolayer graphene from single monolayer graphene, and then use the fact that if you tear off a piece of monolayer graphene from the same layer and twist it and pick up the second one, you can adjust the angle between the two. We have the added difficulty that at the end of the day, we would like to have the STM tip access the surface of our bilayer graphene. And we need that surface to be relatively clean in order to do meaningful STM experiments. So we have to sort of flip this structure that our transport colleagues have taught us how to make. But what typically they do, as you'll find, is to encapsulate their samples in hexagonal boron nitride to protect them. So here's what the samples look like for STM studies. And remember, STM is a needle, and here you really truly are trying to find a needle in a haystack. So this is a fun navigation problem of finding a small flake of a few micron in the STM experiment. So our devices have been continuously improving in terms of their quality, in terms of their cleanliness. Here's some of the cleanest devices that we've been making. And the advantage of the STM experiment, as you can see, is that you can clearly resolve the atomic structure. This is the finer structure that you see here of the top graphene layer. You can see the bright spots here. I showed you so the angle comes from the distance between these bright spots. Right away tells you what twist angle you're dealing with. And also you can see that bright spot having to do with the large density of state of the flat band initially in just any STM topograph. In addition, you see another periodicity in this image, which actually tells you what your angle of your bilayer graphene is relative to the hexagonal boron nitride sample layer underneath, which as I mentioned, is another key parameter in how you adjust the electronic structure of this system experimentally. So just like the initial experiments done almost 10 years ago, if you put your STM tip over the what I call the AA sites on this top layer of twisted bilayer graphene, you see two sharp peaks in the density of state. You notice that here the two sharp peaks is below the chemical potential, below zero. This is the tunneling density of state, dI dV as a function of energy. And this is actually turns out to be critical because here you have both of the flat bands filled. So think of these two sharp peaks as the conduction flat bands and the valence flat bands, and we'll get to how we partially filled them in a moment. But this is how they would appear as two sharp peaks telling you that you have very flat bands as you're near the magic angle. So these are the Van Hoff singularities. Now, very early on, we realized that, us and other groups realized that the strain actually plays a big role in what you measure in the experimental studies in the STM. And this is something that, of course, experimentalists who are doing transport studies or other studies cannot really characterize, but we have the ability to characterize the degree of strain directly from these STM images. So what you see here in this Moiré superlattice structure is that the triangles here do not have equal sides. So this is due to the fact that the layers of graphene are strained as we lay them down. And this strain has an important role to play in the band structure of the system. So we can input the strain, we can model the strain following this nice work from Columbia, and introduce how much strain we have in our device in terms of percentage strain into the Allen's model of, for example, the band structure. And in addition, so one other thing that goes into Allen's model is the ratio of the AA to the BA sites, which we can read off of these STM topograph. So the reason I show this is that it shows that the flat band in the single particle picture, the flat band dispersion of the system is very sensitive to the strain, as you would expect. And in fact, if you take this calculation from the McDonald model for this particular area of the sample, where we have characterized the strain, and compute what the density of state would be, you see that the spectra that emerges actually matches fairly nicely what you expect from the experiment on this same area. You can even see features in the calculation which resembles features in the data as giving you information about where the remote band begins. As we discussed, the remote band can be moved further away. There can be a nice gap between the remote band and the flat bands depending on the strain in the system and the relaxation as well, which is what's being taken into account here. So now let me switch from this point spectra to making measurements of spectra as a function of gate voltage. So just to orient you, what you were looking at were two peaks, which is now translated into two sharp lines in this picture. So here, the color plot represents the density of states. The two flat bands, the conduction and valence band flat bands in the single particle picture are these two lines. And you see here, they are below the chemical potential, which is at 0 here. And as you adjust the gate in this structure, you begin to, when they are full, you begin to deplete them. So I'm going to divide this sort of measurements into 3 different regions. So there is region 1, where the two flat bands are below the chemical potential. You see these two sharp peaks. And then you have region 3, which the two flat bands are above the chemical potential. Again, you see two sharp peaks. You might notice that the height of the peaks can be slightly different from the other side. These has to do with the STM setup points, we believe. But in general, what you're looking at is sort of what you expected from the single particle picture. And you can also notice that as these peaks approach the 0 energy, approaching the chemical potential, these peaks actually get somewhat sharper, indicating sort of like a simple Fermi liquid-like behavior as you bring quasi-particles and make them long-lived near the chemical potential, which you can characterize by this width as a function of how far they are relative to the Fermi energy. They follow roughly this E-squared behavior. But you notice that in the middle, in region 2, which is where all the action is, where you have partial filling of the flat bands, when you plot the spectra, as well as if you just look at the data in this color plot, you see that what was really sharp and prominent as peaks in the density of state having to do with flat bands becomes extremely broad, okay? This broadness you can sort of characterize as looking kind of at the width of the peaks, and it has a very unusual behavior. Of course, this is caused by interaction between the electrons. We kind of know that because we are partially filling the bands where electrons now can interact with one another. What's unusual about this for us is that if you're thinking about interactions, you literally mostly look near the chemical potential, right near the Fermi energy. That's because that's where you have the partially filled band. But here the broadening is actually happening even for a level, in this case, the lower flat band, which is below the chemical potential and should be completely filled. And a similar behavior emerges when we start to deplete the lower flat band, the valence flat band, where the unoccupied upper flat band, which is now above the chemical potential, displays also very unusual broadening. There is actually a point in near charge neutrality, which is this kaon, this particular spectra here, where you see actually they retain somewhat their sharpness, the two flat bands, when they are actually, one is occupied and one is completely empty, right at the charge neutrality point. So in our initial study of trying to understand the spectroscopic property of the system, we try to see if we can devise some sort of a mean field way of taking into account interaction using Hartree-Fock to see whether we can capture these spectroscopic features. And the short answer is that you cannot capture these features from Hartree-Fock. And the way this manifests itself in Hartree-Fock calculations is that essentially interactions broaden the addition removal spectra, which is what you would call these peaks, these Van Host singularities, and then as they become broadened with bandwidth and interaction. And this interaction is somewhat independent of filling as you go through even partially band filling. That's what we find in these calculations. So the question is, why is this failing? And we believe this is because this system is very strongly correlated. So a way you kind of think about our experiment is that we are tunneling electron into this Moiré pattern, which, as you see in these STM images, there are these AA sites with very large density of states of the flat band. So even from the get-go, you can kind of think electrons are going to be very strongly interacting if they're partially occupying inside these quantum dot-like features. You have two flat bands. You can think of them as two different levels. And you can ask yourself, what would the electron addition removal spectra look like if you try to take into account interaction? So in a mean field model, let's see, somehow. Okay, here we go. In a mean field model, of course, if you have no interactions, the width of what you would see in the density of state would just simply be whatever is the broadening of those levels, like the width of the flat band, how much leakingness is happening from these sites, these AA sites. And in a mean field model, if you include interaction, you just simply think about adding energy U to the energy of a particular, the next electron that you add to the system. So here we are just ignoring all the flavor, spin, and valley degrees of freedom. But if you think about partial filling, a mean field will just tell you, oh, you just replaced the answer that you had with just including the probability P for how you partially fill this band. But of course, this is wrong because, in fact, there are two different things that are happening here. Either you have an electron already present with a probability P in your dot, and if you don't, you have probability 1 minus P, and you actually can think about two different processes or two different possibilities in which the system can have not just a single peak, but two peaks. So the way to think about the broadening you see in our experiment when you have partial fillings is that you are basically experiencing all these different charge configuration in the system where the local electrons in the nearby or even in the same dot is fluctuating quite strongly because of the interaction between the electrons. So you can try to make a better model of this. Of course, this is very hard because you're in a very strongly interacting regime. So you can see even STM images kind of inspire sort of a Hubbard-like model of this system where you can think about these bright sites, the AA sites, as sort of where the electrons are localized, hopping between them, and on-site energy, on-site Coulomb, and nearest neighbor interaction. And let me just flash that if you do this in some exact diagonalization calculation with just a few sites, not just 7 sites, because many sites is not possible, you begin to see that in addition to the 2 peaks that you get from the single particle excitation of the 2 levels, you have many other peaks in the system corresponding to these large number of different fluctuations in terms of the charge states of the system. So in essence, this is kind of a baby model, but this sort of splintering of these peaks is sort of like the broadening we see in the experiment. Let me see, I jumped ahead too fast. Sorry, somehow I have to delay my reactions here. So what you see here is that in the experiment, these sort of two very prominent peaks become very broad and multi-features is really kind of reminiscence of the splintering of these peaks that we see in this exact diagonalization calculation. So this was our first indication that we are dealing with a strongly interacting system just from the initial STM experiments. So let me mention that our study appeared basically at the same time with two other studies, one from Stefan Najbergi from Caltech, and one from Abe Pasupati's group at Columbia, in which the experimental broadenings that I've been discussing in observing kind of all the different experiments. It's more prominent when you go through the whole entire gating range to compare the property of the system, which is possible in these two experiments because of the thinness of the dielectric going to the gate in the system. Okay, so now we have begun to make cleaner and cleaner devices, and in this blurry region of strong interactions creating sort of a broadened spectral weight for the electrons in partially filled band, we have begun to see other additional feature in the data. So let me reorient you again. Here what we have are, again, these two lines. These two lines represent the flat bands where they're fully occupied, and that's why they appear as sharp and like a single particle picture. And at this point, they jump to the chemical potential, one of them, and that's when you start to partially fill this band. And if you look carefully at this data, you see as we go through different regions of gating, we have multiple feature, a cascades of feature, which is repeated kind of in a number of different ways. So a way to bring out these fine features in the data is to take DIDV, which is what we measure, and divide it by I over V, which is also measured in the experiment. The reason this helps is because the overall current is changing quite dramatically as you go between different gate conditions, and this is taken out of the data when you plot the data in this particular way. But it basically shows the same thing, and you can kind of see that as we start here at nu equal 4, we have all the full 8 electrons in the system. You have some feature that starts at the chemical potential, moves to some higher energy, and then the system resets itself. So let me show the raw data here so you can see what I'm talking about. So these are the symbols here show the features that I'm focusing on. They are on top of very broadened spectra in here, but they're systematically starting at near the chemical potential, move out to some energy of 20 or 30 millielectron volt. And as you go through integer filling, there seems to be a sudden shift in the property of the system, and the process begins again. And this is observed both in the upper flat band and to a less extent, but still, if you look carefully, also in the lower flat band, when it's going through its transition, moving below the charge neutrality to nu equals -1, 2, and -4. So this is schematically how we think of what we are seeing in the spectra. These are sort of cascade of different transitions. And this has kind of puzzled us as to what are these features that we see in the experiment. Obviously, transport studies had told us that there are changes happening in the system at every integer filling. But here we have spectroscopic information of what's happening. And the question is, what does this mean? Let me just add that these experiments what I'm presenting are done at higher temperatures. If I have time, I can show you some experiments at lower temperatures, but these are above when you get the insulating phases form in the system. So now we can go back and think about what we were thinking before in terms of interacting electrons in this Moiré system, our baby model, and think, is there a way to try to understand this data? So this is again my kind of a poor man's model of quantum dots, if you wish, motivated by the flatness of the band and the localization of electrons on the AA site, nearest neighbor interaction U, and long-range interactions. So now we believe that in order to understand these features, of course, we have to start thinking about spin and valley degrees of freedom in the problem. Clearly, just motivated by the number of sequence of things that we see in the experiment. So the simplest model you can write down is this sort of infinite U Hubbard model, basically ignoring the hopping between them completely, but including the flavored degrees of freedom that you have. So as the theorists in the audience would know, this is, of course, an intractable problem if you put in the flavored degrees of freedom. This is even more complicated than the Coop rates. So you can kind of think of this as at each site, you have two levels, which I call E and minus E naught. These are the two flat bands. And you can basically fill 4 electrons corresponding to the different flavors of the electrons in the system in each of these dots. So you can take this very simple model and compute what should be the electron addition and removal spectra. So let me start here. So this is, I just want to show you what comes out of this simple model and just put it first side by side with the experiment. You can kind of see why now you're motivated to try to understand what this model is telling you, because it's telling to show you the sequence of features, which looks a lot like the experiment. So let's dig a little bit into what are we looking at in this quantum dot model. So let's start at the very bottom here, where we have no electrons in the system, basically at -4. Basically, you have the two levels represented by the different colors bubbles here. And you can think about all the different electron addition and removal excitation you can make in this system. So remember that the possibility that you have 2 electron doubly occupied sites here at almost no filling in the system is exponentially suppressed. Nothing is going to be happening there. And then what you have here is mostly a system where you have, it's quite common to have, the system is almost unoccupied. Okay, it's rare to find an electron in the system because you're very close to -4. I'm going to set the chemical potential here as at 0. Sorry, I think I advanced a little too fast. So what you're looking at here are basically 2 peaks that dominate the spectra. And these 2 peaks are basically corresponding the electron additional and removal that is common in this system. Most easily, you can add an electron with 0 energy here at center here. And of course, you can add an electron into the upper level 2E naught as well. And that's also, there is hardly any electrons in the system to interact with one another. But now imagine you raise the chemical potential, you adjust the gate, the charge density in the system, and you mostly get into a situation where you have almost 1 electron in the system. Now, in addition to 2 peaks that I was describing, you start to see 2 additional features in the data, and that has to do with the fact that you can get excitations with possibility of U, which is what you pay the price to add an electron into the system when there's already an electron in the same level, and 2E plus U, which is to add the electron to the upper level when there is an electron in the same dot, but it's living in the lower level. So what's important about this is that now you begin to kind of see the different features that we see in the data as we adjust the different, the chemical, the gate voltage going through this sequence of integer filling. And what is changing in the number of features that you see in this electron addition removal spectra has to do with what is now the commonly occupied state of the system, whether you have 1 electron or you have 3 electrons or 4 electrons. And here's a level where you have 1 electron for sure. This is now the most common state in the system. And what are the excitation, additional removal spectra in the system? In addition, I should say that once you cross this transition, of course, within this simple model, the chemical potential will have to jump by U. And that's because now you have, on average, 1 electron in the system, and you have to pay the chemical potential U to add an electron to the system. And of course, you can analyze this type of picture in detail, as we have done for all the different fillings. And you can follow all these different features that we see in this model and put them side by the experiment. And you can begin to see that some of the features we see in the data are very clearly related to a sequence of features we see in this very simple model. Now, I should add, the simple model has everything happening very abruptly, which I'll address in a moment. But even if you ignore that and just think about what energy do these features go up to as you adjust the gate voltage, you begin to see that this comparison allows you to make a quantitative measurement of the interaction strength in the system. And this number is 23 millielectron volt. And this is a very large number because it's twice what the bandwidth that we get roughly of this system when the system is in the non-interacting regime.
Ali, can we have a question from the audience? It's actually a theoretical question, so I'm just going to read it off because, it's regarding the cluster extended Hubbard model. So okay. Are only density-density interactions considered, or also exchange-like terms?
No, right. So in the previous model that I showed, there is no, it's just density-density interactions because otherwise it would be too complicated, I believe. I believe the exchange interaction, I'm sorry, yeah, you're talking about, so let me go back.
That question was like 1 minute ago, so.
Yeah. So I think he or she is asking about this model.
The question is from Kang Sung Zhang.
Okay. So in this, let me find it. Yes. Yes, so this was done with a single flavor. So exchange interactions were not included. That's the answer.
Mm-hmm. Okay.
So, but that question leads me to this slide, which is that you can, of course, go back to that type of model and try to add, try to simulate the similar kind of model if you add, for example, exchange interaction, multiple flavors, and include T as well. Now, this one is done with very, very, very small number of sites. I forget, maybe it's like 4 sites. So this is a very small calculation. But the point of showing it here is that while this is a model with just a single site, if you like, with no hopping between the sites where you see sharp features in the data, this model, which includes flavors and multiple sites, it has similar features, but those features are evolving rather smoothly with filling in the structure, which is what we see in the experiment. So we believe that if you do more sophisticated calculations, which goes beyond this simple model, which includes hopping, exact diagonalization, you begin to understand the fine feature of this data even better. So this is, of course, a lot of room for improvement for 3 years working on this problem. But this simple model also gave us another important feature that we started thinking about to look for experimentally. And this was also mentioned in Alan's talk, and I'll make connection to that in a moment. So in this, of course, infinite U Hubbard model, if you, as I mentioned, as you go through these points of integer filling, the system would make a sudden jump in the chemical potential. And this happens because in this small model, you basically, you can think of this as a sort of a Mott states, which you're going through these gaps, which are set by you. Now, the problem here may be more complicated, but this sort of motivated us to say, is there a way experimentally to find a way to extract the chemical potential from our experiments? And so far, I've shown you all the STM experiments that were done with the STM tip, essentially at the AA sites. At the AA sites, which is where this bright spot is where you have the large contribution from the flat band's density of states. And that dwarfs everything else. When you move your tip to the AB sites, the contribution, the density of state contribution from the flat bands is very small, relatively speaking, and you become more sensitive in the tunneling experiments to the remote band. And that's seen right away from, now again, I'm showing you a similar kind of experiment. The colors represent the density of states as a function of gate voltage and as a function of energy. And you see in the middle near the chemical potential, the features of the flat band, which we have been focusing on so far. But now if you look away from the flat band at higher energies above and below, you start to see a lot of signal. And this is coming from the remote band. And what you're seeing here is the edge of the remote band, which is highlighted by this arrow here. you see that as you go through the same gate range of partial filling of, say, the upper flat band and then the lower flat band, you see cascade of features in the edge of the tunneling into the remote band. So what you're looking at here is basically the enhanced density of state coming from the edge of this remote band. And this for us is a very nice experimental observable from which we can figure out what's happening in the chemical potential in the system from spectroscopy. So imagine that the edge of the remote band, of course, has some single particle contribution, which is just comes from single particle calculation of the band structure. There's a chemical potential in the system. You can also add to this a idea that if you put an electron there, it could interact with the electrons in the flat band, which are at the chemical potential. And what you would measure as energy of the excitation, this excitation would be a combination of all these things. And if we anticipate that our system would undergo this sequence of jumps in the chemical potential from this Coulomb interaction physics, that we would be able to see it in this edge of this remote band, which is what we believe we see. So let me extract from this data just the energy of the edge of this remote band, which is done both for the conduction remote band and the valence remote band. And what you see here is sort of almost like a spoon-like shape features. There is sort of a electrons, the energy comes and it has this sort of flattening happening as it goes through each integer filling, which is very nicely seen, for example, for the conduction flat band and the valence flat band here in this regime. So these are the features extracted from this data. You can also see them in the lower part of this data, but they're not as clear as they are in the upper region. For example, here you see very clearly, again, cascade of features, but here is less clear. Now, what's interesting here is that it's basically telling us that the system is undergoing these changes in the chemical potential. So what's plotted here on top is just a raw energy extracted from the remote band edge. And what's plotted here at the bottom is us making a model in which we extract this interaction term, this mean field interaction term from our data to try to put some raw numbers for the chemical potential, which we don't directly measure in this experiment. As Alan mentioned in his talk, there's some recent experiment, actually our experiment and Shahal Ilani's experiment, which Alan showed in his talk, appeared together a few weeks ago in Nature. What Shahal and his group do is they measure using a scanning SCT, the chemical potential, the compressibility of the system from which we can extract the chemical potential. And what is really nice is that if you look at their data, this is data on one of their devices. This is data at some high magnetic field, but they also have data at low fields. If you actually look at the chemical potential that they measure as a function of their filling factor, it looks just remarkably like what we extract from our STM studies of the remote band edge. And even the numbers seems to match in absolute value. So, of course, this has direct connections with what's happening at lower temperatures. So it is, of course, at these points, these cusps, if you like, in the chemical potential is where the insulating phases form as you go to lower and lower energy. And you know, we are not in a position to make a strong claim about whether these are really broken symmetry states, because we have not measured the broken symmetry experimentally in our experiments. But it looks like even before you get to the broken symmetry states, the system knows from these Coulomb interactions, this reshuffling of its electronic states, and wants to have this cascade of changes in its chemical potential, perhaps getting ready for that broken symmetry state to emerge. What's also interesting is that our experiments make direct connection also to the transport studies. There's been a mystery kind of early on about the nature of the quantum oscillations, which was measured, which also show these sort of cascade-like behavior, if you wish, as you change the filling factor. What I mean in particular is the fact that the Landau fans, which were very prominently seen near the charge neutrality, as you go to other fillings of 1, 2, 3, 4 by my definition, you see on one side very nice Landau fans that emerge from the integer filling, whereas on the other side, the Landau fans are somehow missing. And this asymmetry in the slope in the chemical potential as a function of the filling, which is related to the density of states, is what is probably responsible for this asymmetry in the observation of these Landau fans. Of course, if you have very high density of states, it is very hard to resolve Landau fans. It becomes much easier as you go to the system when it has a lower and lower density of states, which is the difference between how you approach, how you come out of this integer filling as we see in these experiments. All right. Now, before I close, of course, you might wonder, is there a way to verify all this that I've told you? You know, I claimed that, you know, interaction is very critical to understanding this data. I gave you this sort of very highly interacting Coulomb dot almost model. This also begs the question, do we need the magic angle to observe this strong interaction? So what's the beauty of our experiments is that we can, of course, hunt around in the same device or across devices and even find regions of the same sample that are not in a magic angle. And that makes even a bad device actually useful for control experiments. So here's a sample in which it's not at the magic angle. And we can basically do the same kind of study that I showed you before. We can look at the density of states. We can look at you can look at the real space map of the experiment and compute basically the single particle picture of what the bands should look like. From the periodicity, we can figure out what the angle should be and put it into the model. And of course, you can see here that the bands are no longer that flat. They actually kind of become somewhat fatter. This is a device at only 1.72 degrees compared to 1.1. And what's nice about this is you can basically repeat all the experiments, and you can see that these sharp features of the flat bands, which show up, well, they're not as sharp as they were near magic angle, but they're still fairly sharp. They actually remain fairly sharp as they go through the chemical potential, as you partially fill these bands that are not as flat as they used to be when you're at the magic angle. These effective strong correlations that I showed you in this experiment, both the broadening in the first experiment and the cascade in the second experiment, they're all gone, okay? So you really need the magic. And this sort of speaks to a point that Alan was talking about, which is that the bandwidth can be very sensitively tuned with the twist angle. And consequently, we can, of course, be at the largest U over T, as has been anticipated theoretically. And there's another thing that I didn't mention, which is also important, and in the transport studies by our colleagues, I think including our chairman, as this has been considered, is the distance between the sample and the gate, and the screening effect of the gate on the interactions. I found it amusing after we measured this number of about 23 millielectron volts in our experiment for the interaction U, and comparing it to this paper by our chairman, in which the theoretical colleagues had estimated the value of U using the Venner function shape and size that people have sort of approximated for magic angle. And they actually find very similar 23 millielectron volt in the regime of our experiments, where the distance to the gate is quite large. So of course, this is something we can also tune in our experiment, which is a knob that we haven't yet tuned. So I think I'm coming to an end. So the key point of this talk is that U is the largest energy scale in this problem at the magic angle. And these cascades that we see are really just a natural consequence of the quantum degeneracy. It could be on its way to spinor valley polarized states at integer filling with zero magnetic field. And of course, there are these nice examples with aligned boron nitride samples where this type of physics in terms of valley polarized states and anomalous quantum Hall states emerge. But this is something that more experiments are needed. And let me just close with this outlook. I guess for us as a group, we just have just scratched the surface of 2D materials with just graphene and twisting. So there is a lot to do in this field. So let me stop there.
Okay, thank you very much, Ali, for the wonderful talk. So actually, we're very good on time. So we have actually easily 15 minutes for questions. So I would invite everybody to raise their hands, and I will try to go one by one with the questions. So I have a question from Maximilian Kogel. So can you? Okay, so it looks like we cannot allow them to.
Oh, I see. There are some questions I see here in Q&A.
Right. So right, exactly. This is what I'm seeing. So somehow we don't have the participants cannot use audio. So okay, so maybe I'll go ahead and I will read off.
Yeah, please go ahead and read the questions.
Some of the questions.
Yeah.
So Pavel Potash asks, in your measurements around -70 and 70, you see large density of states. So I guess this refers to gate voltage.
Yeah, these features.
Right. Yeah. Does it come from remote bands? If yes, how can you explain it as you are on AA, not AB?
Yeah, okay. So I think that there are a few things. I think there is first, there is contribution from the remote band. And there is also contribution from this phonon enhancement in the tunneling that's been seen also in graphene, in tunneling studies by Mike Cromie and some of the other folks, which also contributes to some of these features that are not gate dependent. I believe that's also contributing to this data.
So actually, the speaker, the question can be now answered.
You mean question can be voiced?
Voiced, yeah, it can be voiced.
Yes, do you hear me?
Yeah, we hear you.
Yeah, okay, thank you. How can you explain that it was not observed in previous experiments, and actually I saw it only in one of your samples, not in the other? So what is this sample?
So some of these features can be tip dependent. So phonon addition to the tunneling spectra seems to be very dependent on what kind of tip you make. So I think that some of the features are related to the remote band, but this phonon contribution complicates some of these measurements that appear around 60 millivolts or so. There are experiments by Mike Cromie and Joe Strosio, which have also seen these features in just graphene.
Okay.
You can look at those papers.
Yes, thank you. Maybe one more question. Do you plan to do measurements on twisted bilayer graphene aligned with HBN?
We would like to, yes. I think that we haven't made such samples yet, but that's of course one of the things should be tried by us or other STM groups working in this field, because there seems to be some key differences between those two.
Yes. Okay. Thank you.
Thank you very much. So we have another next question by Maximilian Kogel.
Yeah, thank you very much. So my question is more from an experimental side of you. You said that you use twisted bilayer graphene without top HBN layer. Would it be possible to use like a monolayer HBN? Would you expect that as a top layer, and would you expect that the tunneling current would still be enough to see the Moiré effects?
I think it is possible to tunnel through one monolayer of HBN, but I don't know if you're experimentalists and make these samples yourself, but getting one monolayer of HBN on top of these samples is quite challenging experimentally. But I think it's a challenging thing to make. But I think you can tunnel through one monolayer or one or two monolayers. We have in the past by accident.
Okay, thank you.
Okay, I read one more question by Xing Chen, and actually I'm very interested in the question myself. Did you ever observe superconducting gaps in the spectrum?
Okay.
Rumor has it, right?
Well, we have some data which, you know, is a time of COVID, so we're trying to reproduce these experiments. I have some data. I anticipated this question. So we have some data going to millikelvins. So I'm just going to flash a couple of slides. So here's a device that's been cooled to, it's at the electron temperature of 200 millikelvin. And we see some of these cascade features that I described before, also at lower temperatures. But now you can kind of see these very sharp gaps in these spectra near zero bias. And I'm going to focus in particular around this nu equals -2, which from even the initial study seems to have the sort of the superconductivity was the most robust there near nu equals -2. I don't know whether this is true in your devices, Dima, or not, but this is what I remember from Pablo. Mm-hmm. So here's what the data looks like. Here's the 6.5 Kelvin. This is 200 millikelvin. This is electron temperature. You can kind of see a gap that's very nicely opening up near nu equals -2. This gap seems to sort of be very localized there. This, we believe, maybe the insulating state at nu equals -2. It closes as you dope it away. And then another gap opens up and it persists for quite some time in the system. So this is the nu equals -2 gap. It's about 2 millivolts. It could be the possibility insulating state. And this is the one that we are not sure if it's a superconducting gap, but it looks like one, where it really goes to zero. It's sort of looks like a nice coherence-like peaks, maybe. It's a very large gap. It's like 2 milli-electron volts, 2.8. Mm-hmm. So if you believe this, you would say that, you know, it's a very unconventional BCS-like state. But this remains to be sort of fully vetted to make sure it is really the superconducting gap. So, you know, as you can imagine, measuring a gap is very easy, but to prove that it's a superconducting gap will take some effort.
Mm-hmm. Do we have any more questions? Please raise your hands. Okay, so we have a questions by Dimitri. Sorry. Oh, he raised and he raised again. Dimitri Chihadze. Yep. Chihadze. Hello? Allowed to talk? Okay. Hello?
Yeah, can you hear me now?
Yep.
Yeah.
Okay, good. So in your color plots of density of DOS versus gate voltage, there's an interesting feature that for flat bands in the conduction and in the valence bands, you actually see the different slope as a function of gate voltage and the bias voltage, at least in one of those pictures. So the question is,
are you talking about this slope here?
Yeah, exactly.
Okay, go ahead.
So at least in the previous picture, there are different slopes for the upper part of the picture and for the lower one.
Are you speaking about this part versus this one?
Exactly. Okay. So is there a physical reason for this? And if it is it like the band symmetry, the particle hole symmetry, or it's just some experimental effect which...
Okay, so let me tell you what so as you can imagine, what the slope here, what determines this slope is the number of electronic states you have at the chemical potential which you're filling in order to bring, if you like, the flat bands to the chemical potential as you're emptying in this particular case. So this is indeed relates to what the density of state is in the remote band, if you wish. And if you end up going into its gap, if it has any kind of impurity-like state, if you wish, and how you're filling those states as you bring it in. So I wouldn't be surprised. I don't know how the theorists will feel about this, but I wouldn't be surprised. Let me see if I can bring up, let me see, escape. No, I can't escape. I wouldn't be surprised if so here, I'm just gonna put this up, even though this is not magic. I wouldn't be surprised that the details of the density of states of these remote bands are quite sensitive to the experimental conditions. And that's what's basically determining how fast you're depleting these states, because you're in the remote band and you're removing electronic states. Does that make sense? So there could be, I mean, once you go away from the Dirac point, I think the fact electron-hole symmetry on those large energy scale, I don't think I would not expect any electron-hole symmetry there.
But yeah, but then there will be exactly electron-hole asymmetry, because it will mean that your spectrum for valence bands has different, the gap between the flat bands and the higher
Remote
energy
band.
bands. Yeah, for remote bands would be different on both sides, right?
I've seen some calculation that look like that.
I'm very happy with that.
I mean, I think even in the original paper by Pablo, there was some calculation that the gap to the remote band between the valence band, the conduction band to the remote band was different in magnitude. So I think it depends a little bit on your model, but.
Thank you very much. Thank you.
Actually, we have a very prominent question from Pablo Carrillo himself.
Pablo.
So yeah, so he maybe can clarify the.
Yeah, maybe he can clarify.
Yeah.
Can you hear me?
Yeah, we can hear you.
Barely.
So the electron, there is electron-hole asymmetry even at the level of single particle band structure calculation, and pretty pronounced. So, from the Dirac point, from the charge neutrality point up and down in energy, there is already substantial electron-hole asymmetry. In addition, other types of effects give you extra electron-hole asymmetry, but already at the level of single particle physics, all theoretical models, which include relaxation, etc., they do include very strong electron-hole asymmetry in the gaps, in the shape of the bands, in the density of states. So it's not surprising that things look quite different from the charge neutrality towards electrons and towards holes.
Very good.
Okay, so I might ask just more of a technical question.
Yeah.
So between your first and second paper, was there any clear improvement in device quality, in device fabrication, so that you were able to observe the smaller gaps?
Yeah, I think that there is a lot of cleanliness issue, the early samples, because I think I think the samples were already kind of doped before even we turned on the gate. And I think that we've learned from that. It's still a struggle to make very clean samples. It's not like we can just, put it between boron nitride and not worry about it. Right. It's right in front of our faces. So yes, this is something we're constantly trying to improve.
All right, so I think we're almost out of time, and I don't see any more questions. So I wanted to take, thank you very much, Ali. Thank you again for the wonderful talk. And I just wanted to make a quick announcement. So I was chairing the session today, but of course we have, we will continue to switch chairs. So I just wanted to also thank all the organizers who will continue to chair. So in particular, Frank Kopens, as you know, Adrian Bachtold, Maciek Levenstein, and Antoine Razarbat-Plante, who will chair the sessions in the next couple of days. Special thanks, of course, to Pablo Carrillo, who by his participation also were able to draw so many participants to our Moiré school. And last but not least, who probably did most of the work, organizing this is Robert Sewell from ICFO. So special thanks to him to really make this all happen. And of course, also the ICFO communications team, communications and events teams. And and the way this conference will continue is that basically we will continue to have 2 talks per day, usually starting 3 o'clock Central European time. And then basically almost every day, we will also have a poster on like a short talk session afterwards. So today, if you stay tuned, exactly at 6 o'clock, today at 6 o'clock, we will continue the poster session, which will be moderated by Robert Sewell. And the concept of this poster session will be that every postal presenter will get 90 seconds to make a pitch towards his poster, and then the poster presenters can also meet in a town's chat room where they can actually continue to discuss their posters more in person. I heard somebody making comments. Yep.
I was just going to say, if I didn't get to someone's question, which was on the chat that we didn't get announced, I saw a few. Please feel free to send me an email and I'll answer.
Okay. With this, I think we can close the session. Thank you very much, Ali.
Okay, so we're gonna end this meeting and we'll see you in the poster pitch session. Thank you very much.